Yes.
So, after the revision, my dear students, now let us move and uh, study about the new method for balancing the redox chemical equation. The name of this new method is half reaction method or the ion electron method. In this method, two half equations are balanced separately and then added together to give balanced chemical equation. Let us understand this method balancing the equation in the acidic medium. Suppose we have the equation Fe plus 2 that reacts with Cr2O7 minus 2 to gives us Fe plus 3 and Cr plus 3. So for that, if we really want to understand, let us understand this particular equation and then we can move forward. So let us understand this equation, balancing this equation stepwise. In the first step, write the skeletal equation, assign oxidation number to all the atoms in the reactants and products, and then determine the species oxidized and the species reduced. Then write the oxidation half reaction and the reduction half reactions. So in this first step, what do we do, my dear student, is first we write this equation, then we assign the oxidation number to all the atoms present into the reactants and products. Then we find out the species oxidized, species reduced, and then we are going to write the reduction half reaction as well as the oxidation half reaction. So let us do it without any problem. Here the skeletal equation is Fe plus 2 plus Cr2O7 minus 2 that gives Fe plus 3 plus Cr plus 3. Let us assign the oxidation number for Fe plus 2. For oxygen if we take minus 2, then for Cr it is plus 6. For Fe plus 3 it is plus 3 and for Cr plus 3 it is plus 3. We can see that Fe plus 2 has been oxidized to Fe plus 3 and Cr plus 6 has been reduced to Cr plus 3. So now we have the oxidation half reaction, that is Fe plus 2 that gives Fe plus 3 and the reduction half reaction, that Cr2O7 minus 2 that gives Cr plus 3. In this step, for both the half reactions, first balance the atoms other than hydrogen and oxygen. So in the same manner, first for both the half reaction, we need to balance the atoms other than the hydrogen and oxygen by multiplying either side with the proper stoichiometric coefficient. Then we need to follow the balancing oxygen and hydrogen. Then we need to find out the charges both the side. If the side where positive charge is more, find that side. So first we need to find out the charges and we will find that there must be some side where we will have the positive charge more. So we'll have to find out the side where do we find more positive charge. Suppose we have X positive charge more on one side, then this side where we have X positive charge more, we need to add X electron minus, so the charges will be balanced both the sides. Once again, if there is one side we have X charge positive, then this positive charge extra side, we need to add the same X number of electron so that the charges will be balanced that side. So thus we can balance the charges into the half reactions by adding the required amount of electron and then the charges would be balanced. Here for oxidation half reaction, if we write Fe, that gives Fe plus 3 plus 1 electron, the reaction itself is being balanced because there is nothing more to balance here. Here we have plus 1 more charge, and to resolve this plus 1 more charge we have added 1 electron and this half reaction has been balanced. Now we need to move to balance the reduction half reactions. So first we have Cr2 here and here we have only one Cr. So let us balance atoms other than hydrogen and oxygen by multiplying the right hand side Cr plus 3 with 2. So we write Cr2O7 minus 2, that gives 2 Cr plus 3. Now chromium is balanced. Now let us find out oxygen. In the product side is 7 oxygen, and in the reactant side we have 0 oxygen. So now let us find out oxygen. Product side 7 oxygen deficient. This product side we have 7 oxygen deficient. Reactant side we have 7 oxygen, but product side we do not have any oxygen. So product side is 7 oxygen deficient. So let us add 7H2O to the product side and 14H plus to the reactant side. So let us do this, that Cr2O7 minus 2 plus 14H plus, that gives 2 Cr plus 3 and 7H2O. Now let us check out with the chromium. We have chromium left side 2, right side 2, oxygen left side 7, right side 7, hydrogen left side 14, right hand side 14. Now let us find out the charges. So total charge here is minus 2, and here total 14 into 1, that is plus 14. So the total charge plus 14 minus 2, that is plus 12. Here if you multiply the charges, 2 3s are 6, so it's a plus 6 charge only. So total we have plus 6 charge, here we have plus 12 charge. So here 6 plus 6 charge extra. To balance it, we need to add 6 electron on the left hand side. Here reactant side has plus 6 charge more. So let us add 6 electron to the reactant side. So we need to add 6 electron to the reactant side. So by adding 6 electron to the reactant side, we can write the equation as Cr2O7 minus 2 plus 14H plus 6 electron, that gives 2 Cr plus 3 plus 7H2O. Now if we balance now if we check the charges, minus 2 plus 14 minus 6, that is plus 6. On the right hand side, 2 3s are 6. So total plus 6 charges. So now in the reduction half reaction, we have both the side balances, both the side charges are balanced. Now in the third step, write both the balanced half reactions. So now we need to write both the balanced half reactions together and see the number of electrons in both the reactions. Take LCM of the number of electrons, and then, so first we need to find out the number of electron, then we'll have to take the LCM of the both the electron, and then multiply both the half reaction with suitable number, so that the number of electrons in both the half reaction become equal. So let us do it so that we can understand better. Now add both the half reactions and cancel the number of electrons from both the sides. After addition, we get the balanced chemical equation. Confirm the balanced chemical equation by checking the charges both the sides. So here we have the oxidation half reaction Fe plus 2, that gives Fe plus 3 plus 1 electron, which is balanced half reaction. The another reduction balanced half reaction is Cr2O7 minus 2 plus 14 electron plus 6 electron, that gives 2 Cr plus 3 plus 7H2. You can see that in one reaction we have 6 electron, in another reaction we have 1 electron. So the LCM of 1 and 6 is 6. So here this reaction has to be multiplied with 1, and this reaction has to be multiplied with 6. So let us multiply the oxidation half reaction with 6 and reduction half reaction with 1, and then we add it. So when we multiply this reaction with 6, we write 6 Fe plus 2, that gives 6 Fe plus 3 plus 6 electron. When we multiply this reaction with 1, we write Cr2O7 minus 2 plus 14H plus 6 electron, that gives 2 Cr plus 3 and 7H2. So now we have both this equation having the same number of electron, which we can remove from both the side and write the final equation. Cr2O7 minus 2 plus 6 Fe plus 2 plus 14H plus, that gives 2 Cr plus 3 plus 6 Fe plus 3 plus 7H2O. Now let us check the charges both the side. You can see that the charges on the left hand side is this is minus 2, 6 2s are 12, which is plus, and 14 1s are 14, which is plus. So total 24 plus charge. Here you can see that 2 3s are 6, so plus 6, 6 3s are 18, so plus 18. So total plus 24 charges. Both the sides the charges are same. So the equation is balanced, and we can write the finally balanced equation as Cr2O7 minus 2 plus 6Fe plus 2 plus 14H plus, that gives 2Cr plus 3 plus 6Fe plus 3 plus 7H2O. So this is the equation we have balanced into the acidic medium. Now let us see one more example which is in the basic medium. So let us solve one more example in the basic medium. Let me read the question for you first. Balance the following equation in basic medium using ion electron method. So here we need to use the ion electron method. The equation with us is N2H4 liquid plus ClO3 minus, that gives NO plus Cl minus. This is what the equation that we need to balance. To balance this equation, first we need to write the skeletal equation, and then we need to identify the, or we need to assign the oxidation number to each and every atom. So we write N2H4 plus ClO3 minus, that gives NO plus Cl minus. For nitrogen, or for hydrogen, plus 1 charge. So for nitrogen it is minus 2, for chlorine it is plus 5, and oxygen minus 2. In NO, oxygen minus 2 and N plus 2. Here I have just made a very silly mistake. It is minus 2 here, and nitrogen is plus 2 and Cl is minus 1. You can see that nitrogen from minus 2 it has come to plus 2, so it is oxidation, and from Cl plus 5 it goes to minus 1, so it is reduction. So now we can write the oxidation half reaction and reduction half reaction. For oxidation half reaction we write N2H4, that gives NO. So now first we want to balance nitrogen. Left hand side it is 2, so right hand side we need to multiply it with 2. So we get N2H4, that gives 2NO. Now my dear students, we can find out the number of oxygen. So here we have 2 oxygen and here we have 0 oxygen. So this side is deficient into the oxygen, and some 2 oxygens are deficient. To balance, we will have to add 4 OH minus this side and 2 H2O this side. So finally we can write N2H4 plus 4 OH minus, that gives 2NO plus 2 H2O. Now if we look at the oxygen, 4 oxygen this side, 2 plus 2, 4 oxygen this side. Now if we look at the hydrogen, 4 hydrogen plus 4 hydrogen, total 8 hydrogen. Here we have 2 to the 4, so only 4 hydrogen. So this side is deficient with the hydrogen. Now we have seen that the deficient side should be added to the equal number of H2O, and the same number of OH minus are added to the opposite side. So here on the product side we are going to add 4H2O, on the reactant side we will add 4OH minus. So we will write N2H4 plus 4OH minus plus 4OH minus, that gives 2NO plus 2H2O plus 4H2O. So finally we can write N2H4 plus 8OH minus, that gives 2NO plus 6H2O. Now let us find out the number of oxygen both the side. Left side oxygen 8, right side oxygen 8, left side hydrogen 4 plus 8, that is 12, and right side hydrogen 6 2s are 12. When we look at the charges, we find that on the left hand side we have minus 8 charges, but on the right hand side we do not have any charges. So here we have minus 8 charges this side. So to balance the charges, we need to add 8 electron minus this side, so that we have both the side equal charges, minus 8 minus 8. So let us balance the charges by adding 8 electron to the product side. So finally we can write N2H4 plus 8 OH minus, that gives 2NO plus 6H2O plus 8 electron. Now my dear students, even if we look into the charges, here on the left hand side we have 8 minus 8 charges, and even on the product side we have minus 8 charges. So now we have this equation balanced. Now we can move to the another half reactions. So reduction half reactions, if we look into, we will find that ClO3 minus, that gives Cl minus. Both the sides Cl are same. So on the left hand side we have 3 oxygen. So to balance, on the left hand side we will add 3 H2O, and the opposite side we will add 6 H2O, because this side is oxygen deficient and 3 oxygen deficient. So we will add 6 OH minus to right hand side and 3 H2O left hand side. Now if we look into the oxygen, 3 oxygen plus 3 oxygen, 6 oxygen, and 6 oxygen. If you look into the hydrogen, 3 2s are 6. Here also 6 hydrogen. Chlorine is 1 and 1 both the side. If you look into the charges, here we have only -1 charge, but here -1 plus 6. So -7 charges. So here we need extra -6 charges. So to balance the -6 charges, from this side we need to add 6 electrons. So let us add 6 electrons to the reactant side. Reactant side -6 charges needed. So let us add 6 electron reactant side and we get ClO3 minus plus 3H2O plus 6 electron, that gives Cl minus plus 6 OH minus. So this is the balance half reactions for reduction. Now we'll write the balance half reaction for the oxidation and find out the number of electron both in both these cases. So for this we have 6 electron and here we have 8 electrons. So the LCM for 6 and 8 is 24. So my dear students, the reaction where we have 6 electron has to be multiplied with 4 and the reaction which has 8 electron has to be multiplied with 3. So by multiplying this, we can write the reaction once again. You can see that I have written the reaction of for ClO3, 4 ClO3 plus 3 4s are 12 H2O plus uh, 6 4s are 24 electron, that gives 4 Cl minus plus 6 4s are 24 OH minus. Same way for this, by multiplying 3 we can write 3 N2H4 plus 8 3s are 24 OH minus, that gives 6 NO plus 6 H2O, 6 3s are 18 H2O plus 24 electron. So now we have both the side 24 electron which we can remove easily, and here we even have 24 OH left hand side, 24 OH minus right hand side. On the left hand side we have 12 H2O, on right hand side we have 18 H2O. So this is what we need to remove. So by removing this uh, uh, 12 H2O minus, so 18 H2O minus 12 H2O, so right hand side we will have 6 H2O left with us, and this OH minus both the side equal, so that can be easily removed, and finally this 24 electron can also be removed. So those species that can be removed, I have underlined them with the green pen, and then we can write the final equation. 3N2H4 plus 4Cl O3 minus plus, see this H2O will also be removed and here we will have 6 H2O, so that we can even not write. So 3N2H4 plus 4Cl3 minus, that gives 6NO plus 4Cl minus plus 6H2O. If we find out the number of nitrogen, it is 6 both the side. If we find out the number of hydrogen, that is 4 3s are 12 and here 6 2s are 12. If we find out the number of chlorine, here there are 4 chlorine, here even we have 4 chlorine. If we find out the number of oxygen, 4 3s are 12, here 6 and 6, total 12. And if we find out the number of charges, 4 into -1, that is -4, and 4 into -1, that is -4. So this is the equation which is balanced chemical equation for us. So this is how we can have the balanced chemical equation. 3N2H4 plus 4ClO3 minus, that gives 6NO plus 4Cl minus plus 6H2O. Now we want to study redox reaction as the basis for titration. So here we want to study about the redox reaction as the basis of titration. Let us study the redox reaction as the basis of titration. In acid base titration, as we use some of the indicators to track the or to determine the end point. So, you know, when we add acid to base or when we add base to acid, and if we take the phenolphthalein as a indicator, and phenolphthalein give a pink color in the basic medium. So if you add uh, phenolphthalein to acid, there will be no color, and then if you add slowly the base, when the titration completes, when the acid and base give salt and water, when the neutralization takes place, just after that, if even if you add a single point of base, there will be pink color produced, and this is how we can determine the end point. So when the pink color is being produced, we can say it is the end point. Similarly, into the redox system, or when we do the redox titration, The same method can be adapted to determine the strength of reductant and oxidant using the redox sensitive indicators. So there are two methods which are possible here when we do the titration. Number one, or situation one, in one situation, the reagent itself is the intensely colored, for example, potassium permanganate. Potassium permanganate itself is a violet colored uh, solution. So when we use this violet color solution, we can use it as an indicator. So it's a self indicator into the redox titration. Here MnO4 minus act as a self indicator. The visible endpoint in this case, the visible endpoint in this case is achieved after the last of the reductant, that is Fe plus 2 or oxalate ion C2O4 minus 2 ion is oxidized, and the first lasting tinge of the color appears. So my dear students, if we take the Fe plus 2 ions or oxalate ions in a conical flask, and then we keep on adding the potassium permanganate solution from the burette drop by drop. When the pink color is produced, we can say that the end point has been achieved, and by getting this pink color of the potassium permanganate, here the when the titration end, potassium permanganate itself gives its own pink color, and that is why we call that potassium permanganate behave here as a self indicator. So the lasting tinge or the end point can be easily obtained by using the potassium permanganate for the redox titration. At MnO4 minus concentration as low as 10 to the power minus 6 mole per decimeter cube, or 10 to the power minus 6 mole per liter. Now what does it trying to say? That at end point, even if the concentration of KMnO4 is 10 to the power minus 6 mole per liter, we start getting the pink color, and that is why KMnO4 is a wonderful indicator for the redox titration, especially in case of the redox titration of Fe plus 2 to Fe plus 3 or oxalate ion, my dear students. So this is how we can, this ensures a minimal overshoot. That means even a very small amount of indicator gives us color, and that is why we can avoid the extra addition of the indicator. And in color beyond the equivalent point, the point where the reductant end, the point where the reductant and oxidant are equal in terms of their mole stoichiometry. My dear students, this text simply tries to tell you that when the end point is achieved, even a concentration of 10 to the power minus 6 mole per liter of KMnO4 gives us the clear indication of the end point, and that is why, my dear students, this is a wonderful indicator for the redox titration, and the extra addition of the potassium permanganate can be avoided by a very small pink color, and this is how the titration can be done without any extra overshoot, and thus the rest of the calculation is done. Now in the situation 2, when we are not using the self indicator, if there is no dramatic auto color change as with the MnO4 minus titration, there we need to use indicators. So what is the name of the indicator that we can use? We can use diphenylamine as an indicator. In case of the dichromate ion, which is colorless, diphenylamine produces an intense blue color at the end point. So instead of the KMnO4, if we are doing the titration for the dichromate ions, we can use diphenylamine as an indicator, and we can get the sharp end point in this case. Now we have the situation 3. There is yet another method. This method is restricted to the reagent that can oxidize iodine ions, for example Cu plus 2. So we can use this third method only when we have the reagent that can oxidize iodine ions to the I2. So this method is restricted only to those substances which can oxidize iodine ion to the I2. But a very good example is our copper plus 2 ion, which can easily oxidize iodine ions to iodine. So 2Cu plus 2 reacts with 4I minus to produce Cu2I2 and I2. So this method relies on the fact that iodine itself give an intense blue color with the stars. Please remember that iodine gives the intense blue color with the stars and have very specific reaction with the thiosulfate ions, that is S2O3 minus 2 ion, which is a redox reaction. So iodine, when it reacts with the thiosulfate ion, it produces 2I minus ion and S4O6 minus 2 ions. I2, though insoluble in water, remains in the solution containing Ki or Ki3. So iodine, as it was insoluble in water, it remains in the solution in the form of Ki or Ki3. On addition of stars, after liberation of iodine from the reaction of Cu plus 2 ions on iodine ions, an intense blue color appears. So in the presence of iodine, the blue color appears in the presence of stars. Iodine produces the blue color when it is oxidized from I minus to I2. This color disappears as soon as the iodine is consumed by the thiosulfate ions, and thus the endpoint can easily be tracked. Now you can see that when we start the titration or the redox titration of thiosulfate ion and iodine, before that we produces this blue color with the stars, and then we start adding this aqueous solution of thiosulfate ion. When this iodine present here is completely consumed, the blue color disappears and we get endpoint in that case. So this is how first we generate the blue color with iodine, and then we consume this iodine available by the thiosulfate ion, and this is how the blue color disappears. And we can identify the amount of iodine consumed. This color disappears as soon as the iodine is consumed by the thiosulfate ions, and this is the endpoint that can be easily tracked. Now, limitations of the concept of oxidation number. So in all these chapters, we have studied about the latest information as the oxidation number, but this oxidation number method may also be outdated soon, because new information has been obtained into the chemistry, and an advancement into the chemistry have created the new horizons for the oxidation and reduction information. So let us see what are the limitations of this oxidation number method for this purpose. Let us see. The concept of redox process is evolving with the time. This process of evolution is continuing. So still the process of evolution is going on. In recent past, the oxidation process is visualized as the decrease in the electron density. In the second chapter, we have studied that, my dear students, that now we have been using the various methods which are based on the Schrodinger's equations. So here in this method, we understand everything on the basis of the electron density. So my dear students, if there is a slight increase in electron density, my dear students, we call it reduction. And if there is a decrease in electron density, we call it oxidation. So here, my dear students, the new horizon or the new concept comes into the existence, which visualize oxidation as a decrease in electron density and reduction as the increase in electron density. So, you know, the complete transfer of electrons may be considered as a problem, and just the increase or decrease into the electron density can be considered as a oxidation or reductions around the atoms involved in the reaction. So, according to the new concept, which is different from the oxidation number concept, it says that around the atom which is involved into the chemical reaction, if there is slight increase into the electron density, it is reduction of the atom, and if there is slight decrease into the electron density, that is what it is, the oxidation of the atom. So this is how, my dear students, we complete the discussion about this chapter to the limited syllabus of these years. Now, if you have any doubts, you can ask me.